My name is Ismail Limadri from Stanford, and I will be speaking about LassoNet, a neural network with feature sparsity. This is joint work with Fangruan and Rob Tipshuran. In most of modern machine learning, we use larger and more complex models to deal with ever-increasing amounts of data. And one recent example has to do with a computer vision competition where the best performing model has really evolved towards below a human error area. And the achievement shown in this picture was only possible due to the advent of neural networks, which 10 years ago were not used at all and did not perform so well. However, deep learning can really go much beyond just this computer vision setting, and there's all sorts of other areas where it has provided state-of-the-art improvements and performance. In this talk, I will come back to the age-old classical setting of biological data, for example, that is a lot more structured, where the rows and columns have a very clear meaning, such as individual observations and then gene expression values, with an outcome of a supervised prediction task. And I will approach this problem by taking the existing methods that are based on deep learning and introducing regularization through feature selection. This can provide a number of added values, including interpretability, and is especially relevant when the number of features to measure is large and expensive or difficult to collect, such as protein data. In an example like this one shown here, we see that with just 40 features, we can recover almost 90% of all the predictive power. And this is really a classical steeply concave curve that explains why feature selection has been so popular and why it's often a key pre-processing task in modern machine learning. There's been a lot of other feature selection methods studied in the past, and the goal that really we're trying to achieve here is to have a method that is really well suited for all sorts of arbitrary nonlinearities and has a regularizing property. The way we do that, I will show, is essentially based on using a modification of the lasso. But before getting there, I'm showing the results on just the MNIST dataset, where we see the performance for varying number of features. The method is based on the so-called hierarchy principle. The idea here is to give prominence to the linear part of the model over the nonlinear part. And this can help with regularization in settings where we have either excess data or where overfitting can be a concern. Our approach is that of using a residual or skip connection in the network as the linear part, and to use that to essentially control the rest of the model. So that leads to an objective function that has the usual loss with an L1 term that is only applied to the linear or residual component, together with a constraint that enforces a hierarchy between the linear and nonlinear parts. And in this way, we can achieve efficient feature selection. The training loop is essentially doing gradient descent in a vanilla way using stochastic gradient descent, and I've shown the results here over an entire feature selection path. This is really one of the key differences between our method and existing work that takes as given the number of features to select. In many problems, the number of features to select cannot be known in advance and has to be determined in an adaptive way. This is where our method comes into play and essentially is able to train the model over the entire feature selection path at a cost that is just that of training the model over a single point in the path. And this is achieved thanks to an efficient hierarchical proximal operator that basically solves a non-convex optimization problem and yet finds a solution, an exact solution in an efficient way, so that the overhead over existing over existing cost and work, which is just to compute the gradients, is really negligible. And this can be implemented in standard deep learning frameworks by adding just a few lines of code. We show in the paper that the results are very competitive when compared to state-of-the-art feature selection methods. And I will emphasize once again that most other feature selection methods take as input the number of features to select, whereas the method can really provide the entire path essentially for free. More details on the method, including extensions to unsupervised setting and many others, are available in the paper. We have also made available a poster, and I will end my talk here and thank you for your attention.